Right, hello everyone. Welcome to today's AATN seminar. Our speaker today is Rayna Andreeva from University of Edinburgh, who will be talking about metric space magnitude and generalization in neural networks. The floor is yours.
Hello, thank you so much for giving me the opportunity to speak here, and thank you so much for allowing me to reschedule. So in today's talk, I will talk about applications of magnitude to machine learning. And this talk is based on a joint work with Katharina Limbeck, Bastian Rick, Benjamin Dupuy, Tolga Birdau, and Umut Shimshekli. So let's start with a simple visualization exercise. So let's start with a bunch of points and think about what happens with these points when you zoom in. Depending on the scale, the space will look different. The spatial pattern is changing, clusters are emerging and disappearing until all points have become their own clusters. What magnitude gives us is a way to express the spatial patterns in a compact way. It's a way to quantify the distribution at different scales. And as you think about it, this is quite powerful in its own right. This sort of interpretation of magnitude can be very useful for machine learning. So if we can understand magnitude better, then we can find very fruitful applications for understanding fundamental properties of neural networks and try to provide answers to very important theoretical questions in deep learning. In this talk, I will demonstrate exactly how. The plan for the talk is to start with defining magnitude. Then I will provide an overview of existing application of magnitude to machine learning. Then I will focus on two applications about quantifying generalization. In the first one, we would be applying magnitude dimension to characterize generalization. And in the second one, we would be applying a quantity called positive magnitude to measure generalization again. So in this, if you go back to the first example, in these applications, what we think about of these points is in some points in very high dimensional space that are machine learning models. Let's start with explaining what is magnitude. So first we need to know what is a similarity matrix. So say that you have a finite metric space with distance metric d, then you consider all the distances between your points and you form the similarity matrix where each entry is the exponential to the power of minus the distance between the points. This is the definition of the similarity matrix. Then now that we have this, we can proceed to define magnitude, which is defined as the inverse of this matrix and summing over the entries of this inverse. For the purpose of this talk, we would be focusing on quite nice spaces like finite subsets of Rn. And what is really cool about this is that the similarity matrix is a symmetric positive definite matrix. And as a result, this inverse always exists. And hence, magnitude is well defined. This concept is best illustrated with examples. So let's start with a very simple example, the two-point space. Say that you have 2 points distance d apart. And what we are doing here is we are varying the distance between the points. So imagine when the distance between the points is small, then these 2 points are going to be very close to each other and they would be practically indistinguishable. So we can say that we effectively have 1 point. On the opposite, when d is large, the 2 points become quite far. They're very distinctive. They're their own clusters. And we can say that now we have 2 effective points. So how does that work in terms of the formulas I mentioned first? So we first formulate the similarity matrix. It's just the matrix with ones on the diagonal because the distance between the point and itself is 0 and e to the 0 is 1. And we have e to the minus d on the off-diagonal entries. Then we proceed to find the inverse, so just trust me that this is the formula for the inverse. And therefore, summing over the entries, we arrive at 2 over 1 plus e to the minus d. Now, when d is very small in this case, as d goes to 0, as d goes to 0, we get that the magnitude is 2 over 1 plus 1, so magnitude is 1. And when d goes to infinity, we get that magnitude is 2 over 1 plus 0, so 2. So we recovered what we initially demonstrated, that we have the effective number of points at different scales. Now let's go one step further and consider the 3-point example by Simon Willerton. Let's place 1 point x, distance 1000 t apart, to our original points. And again, let's play the same game. What happens when we vary t? When t is very small, the 3 points are going to be, again, very close to each other and almost indistinguishable. So again, we effectively have 1 point. Now, consider when t is large, then again, the points are very far away from each other. We have 3 effective points. And the more interesting part here is what happens at an intermediate scale, such that y and x are still close and they still look like 1 point, and x is far apart. So in this case, we recover a magnitude of 2. So we have 2 effective points. And this is what this magnitude is measuring. Now let's define what is the magnitude function. So first we need to say what is the scaled metric space with the same points as x. So this is just the same metric space, but where the distance between each point is scaled by a factor of t. And hence the magnitude function is the function from the reals to, so the non-negative numbers to the reals. And this is just taking magnitude over various values of t. And let's go back to our original example. Now that we are a bit more familiar with the scale parameter, we can revisit it and see that, again, for a small value of t, we have 1 point. For an intermediate value of t, in this particular configuration of 5 points, we recover 3 clusters. And when t is large enough, we recover the cardinality of the space. Okay, so now that you know what is magnitude, let's say what magnitude has been applied to. So the concept of magnitude originally popped up in theoretical biodiversity, in theoretical ecology, and the point was there to quantify how diverse species are. After that, the first application of magnitude to machine learning was considering magnitude weights as boundaries for machine learning and detecting outliers. There has been also an application of magnitude for edge detection. There has been a more recent application of magnitude for clustering in the PhD thesis of Miguel O'Malley, and a number of more applications of magnitude for optimization. The applications in which we are the most interested in now are the applications of magnitude to deep learning. And here I'm going to talk about 2 different papers. In the first one, we link the magnitude dimension to neural network learning theory. And in the second, we consider magnitude and positive magnitude for the same problem in learning theory. If there is time, I would really like to also talk about the magnitude for measuring diversity in later representations paper. Now, let's consider the problem that we are trying to solve. So say that you have a bunch of points from 2 different classes, or in this illustration, 2 different colors. One is purple, the other one is yellow. And the problem here is about trying to separate these points in such a way that the majority of one class are on one side of this boundary, the other class is on the other, and you minimize the number of different color points on either side so that each point is kept with its own color. So in more general terms, what we are talking about is the generalization capabilities of neural network or machine learning algorithm, but in this case, let's talk about neural networks, or how well a neural network learns. The problem is that these theoretical properties have not been very well understood. A lot of researchers are working in this active field, and they're trying to understand what, how, and why a neural network learns. And one way to do this is to study the generalization error. which in a more broad terms is the difference between learning and simply memorizing the data points. So the main goal of this work is to demonstrate that there is a connection between the generalization error and magnitude dimension. And if there is one key takeaway that I want you to take from this part of the talk, it is that the lower the magnitude dimension, the better the generalization. Now let's try to formalize what each of these words mean. I would assume that not all of you are familiar with machine learning, so let's try to explain in very simple terms what the main ingredients are so that you can understand the rest of this talk. So in a typical setting, you have a training set. Let's start that you start with an input. And the very common input is, for example, the data set of handwritten digits or MNIST. Then you pass it to the neural network and you use the training algorithm to output the best possible function such that when you pass in new input, a new digit, it's going to be classified correctly. So what happens is that you pass in the training images, they go through the network, you have a loss function in the end, which tells you how well you're doing. And then you go back to a process called backpropagation and you update the weights of your function. So you get some feedback on how well you're doing and you keep iterating until you are happy enough with the output. So that you're happy that your neural network has learned, for example, how to tell the difference between a cat and a dog. And what we are focusing on here is the weight. So to each edge, you have you're assigning a weight. And when you stack all the weights together, they form one very high dimensional vector. And at each step of your training algorithm, you have one iteration of the algorithm, and you are collecting all of these iterations into a very high dimensional point cloud. So we would be calling this the training trajectories. Let's give a bit more formalism to what we just talked about. And the most important point here is to define the generalization error. So here we consider the true risk, which is the expected value of all the points over the loss function, and the empirical risk, which is the only thing you actually have access to because you have a finite sample in your dataset. And the generalization error is considered to be the difference between this empirical risk and this true risk. And what is really interesting about these trajectories is they tell us something about how well the neural network learns. And the important observation that the researchers have made before is that the less complex this training trajectory, the better the generalization. So the main question here is how exactly do we quantify complexity? And the answer is by using fractal dimensions. There has been previous works showing that these training trajectories have a fractal dimension. So if we focus on the example on the right, when the fractal dimension is small, this trajectory is quite simplified, and as you increase the fractal dimension, the complexity of the trajectories increases, and you have this quite chaotic trajectory. So I would assume that not all of you are familiar with fractals. So let's try to simply explain what fractals are. One possible interpretation of fractals is in terms of how much space does object take in space. So for example, in this image, if we start with a line and we increasingly, we start bending it in such a way that we form the Koch snowflake, we increasingly take more and more space until we get to the right side and we are in 2 dimensions. So this is the intuition here that the more space you take with this fractal, then the higher this complexity is, or the fractal dimension. And another way to look at fractal dimension is in terms of volume and how many copies fit inside the same volume. So let's first start with a very basic notion of dimension. So when you have, when you are in 1 dimension and you have a line and you say you scale it by a factor of 1/2, then the question is how many copies would fill the original space? So the answer is 2 copies. If you scale it by a factor of 1/3, you get 3 copies. Let's go 1 dimension higher in 2D, where you have a square. You scale each side by a factor of 2, and then 4 copies cover your original square. Similarly, when you have a factor of 1/3, then 9 copies cover the square. Let's go a dimension higher, and in 3D, you have a cube. We play the same game. We scale by a factor of half. You have 8 copies of the smaller cube inside, 8 smaller cubes inside the bigger cube, and let's scale by a factor of a third, and you recover 27. So then basically the dimension is s to the power minus d equals to n. When we solve for this, then we recover the dimension. And this is always an integer in this case, but when we want to generalize this to subsets x of Rd, then we have to apply the same idea. So let's cover x with a grid of boxes of length r, and let's have nr to be the minimum number of such boxes that are covering your shape. Then a common way to measure how fractal your structure is by using the upper box dimension or the Minkowski dimension. Here, a nice illustration of how this works is if we consider the coastal line of multiple countries. If we start with the coastal line of Britain and we start with large size squares, we count how many squares cover it, then we keep decreasing the size and we count again how many squares cover it, and we recover the Minkowski dimension by taking the limit of as delta goes to 0 of the sup of log of the number of covering squares over log of 1 over delta. And what is interesting here is that there's been a paper measuring these fractal dimensions, and the west coast of Britain has the highest fractal dimension of 1.25. After that, it's Germany, and also Australia has the lowest fractal dimension. So now that we are a bit more familiar with what fractal dimensions are, we need to know that there are multiple notions. Minkowski dimension is not the only one. Other fractal dimensions are the persistent homology dimension and the magnitude dimension. And what is really interesting is that they all coincide for compact spaces. Let's start with defining what is the persistent homology dimension. I would make my assumption here, and I would assume that you are all familiar with persistent homology. So in order to define this dimension, we first need to know what is the alpha weighted lifetime sum. So here that is defined by taking the length of all intervals. We're just going to focus on homology in degree 0. So we just take the length of all the intervals and scale it to the power of alpha, and we sum over, and this is the alpha weighted lifetime sum. Now, the definition of the dimension is a bit more technical and more difficult to understand. So what it is the smallest value of alpha, such that for every finite subset of your space, this sum is bounded. Compared to the complexity of the persistent homology dimension, magnitude dimension is quite a bit simpler to understand, perhaps, because it's defined in a similar way to the Minkowski dimension. So you just take the limit as t goes to infinity of the log of mag tx over log t. And a simple way to estimate it, sorry, you can see my mouse, is to, so once you compute your magnitude curve, then you look at the log-log plot and you find the longest line segment, compute the slope of it, and this should be a good enough approximation of your dimension. So what is really interesting is that it has been shown all of these dimensions are the same. Kozma and Schweinhardt have shown that Minkowski dimension equals to persistent homology dimension of degree 0. We always just talk about degree 0 in this talk. Then Mikis has showed that the Minkowski dimension equals to magnitude dimension, and then it's not difficult to see that the persistent homology dimension equals to the magnitude dimension. So why is this important? Work by Birdau et al. Has demonstrated that in fact there is a link between the persistent homology dimension and the generalization error. This is an intimidating looking equation, and you don't need to know what the rest of the terms are. We are only going to be focusing on the topological dimension. And what this tells us that the smaller this topological dimension, the better the generalization error should be. And in this work, what the main observation we made is that since this persistent homology dimension equals to magnitude dimension, then we can obtain, say, a similar bound, but in terms of magnitude. And what is really cool about this is that this kind of opens up the entire area of machine learning theory of exploration using magnitude. So to reiterate of what we are doing here, we are looking at the training trajectory of a neural network. We are computing the magnitude curve, and then we are estimating the magnitude dimension. So how well does this work in practice? We have evaluated the magnitude dimension over a number of different neural networks, training settings and datasets. We have used, and then so for each one of this, we have computed magnitude and also estimated the magnitude dimension. So how well does this work? So here on the x-axis, we see the test accuracy. On the y-axis, we see magnitude dimension. And what we have observed is that the lower this dimension, so the lower this dimension, the higher the test accuracy. And this holds across multiple different data sets and also neural network architectures. Then the next question we wanted to ask was, what happens if we use just magnitude? So basically, because we have more intuition about what this tells us about the space in terms of effective number of points, then what happens here is that we fix a scale for magnitude, and then we plot it against the test accuracy. And what we observe is that consistently across multiple scales, like the better models or the models with better generalization would have a lower value of magnitude. So yeah, and this holds across the different scales of t. And if we have to rephrase this in terms of the original intuition of magnitude capturing the effective number of points, so here magnitude is capturing the effective number of models. So the smaller this number, the better the generalization. The next important question to ask is, okay, how good is our estimate of this dimension? And what we looked at was alpha Levi stable process in which the fractal dimension is known. So when the fractal dimension is smaller, you observe simple trajectories, and as it is increasing, the trajectories rise in complexity. So we also wanted to compare the magnitude dimension with the persistent homology dimension. And what we observed was that the magnitude dimension here in orange correlates well with the ground truth value. However, it was always lower than the ground truth and also the persistent homology dimension. So exploring this difference is the subject of future work. So let's reiterate what the contributions are. So we provided a novel theoretical bound on the generalization error via the magnitude properties of the training trajectories. We further explored the training dynamics using magnitude, and we verified our claim empirically to support the theory. Next, so we noticed this thing about magnitude, but we didn't have a theoretical justification for it. So in a follow-up paper, where we are solving the same problem here about generalization. And what we wanted to do was understand generalization in terms of magnitude from a more theoretical standpoint. Further, the existing topological bounds in the literature are based on notions of fractal dimensions. And in fact, when you have a discrete time algorithm in practice, you only have a finite number of iterations. So it is more accurate to compute a quantity over this finite number of samples of trajectories. And also previous works in this domain have only considered small models and a limited number of datasets. So the main goal here was to demonstrate a connection between the generalization error and the building blocks of both persistent homology dimension and magnitude dimension. So what are the building blocks of these dimensions? If you remember from a few slides ago, for persistent homology dimension, this is the alpha weighted lifetime sum, which is just the sum to the power of alpha of the length of the bars in dimension 0. And what we introduced is a quantity called positive magnitude. So what I didn't tell you was that magnitude is also defined in terms of weights. So each point is assigned a weight. So this is basically the sum over the sum of the rows of the corresponding to this point of the inverse of the similarity matrix. So one thing about these weights is that they can also be negative. So in this work, we considered what happens if you only take the positive values, and we define this quantity called positive magnitude. What is interesting is that as you are increasing the scale t, magnitude and positive magnitudes are the same. However, we didn't further investigate the theoretical properties of positive magnitude. So what we managed to show is we managed to prove two generalization bounds in terms of this topological complexity. One of them in terms of E1, we fixed alpha in the alpha weighted lifetime sum to be 1, and the other one in terms of positive magnitude. So again, we have the same pipeline. We are analyzing the training trajectories, and we are computing our complexities on that. So here, we are not only looking at the weight space, but we are also considering the loss landscape space. And here, in previous work, there has been a data-dependent pseudometric that we use. This is a visualization of a loss landscape, and we are considering distances in this setting. But our framework is flexible, and we can also use other distances and other notions of metrics as long as they satisfy a number of simple conditions. So let's look at some results. What we did here is we scaled to models with millions of parameters, like vision transformers. And we didn't only restrict ourselves to the image domain, we also explored what happens when you also use graph neural networks. So here in the plot on the left, we have on the X and Y axis, we have a thing called granulated Kendo coefficients, which are a way to measure generalization in a robust way. So what one needs to have in order to be sure that they are truly measuring generalization is a high value on both the coefficient with the batch size and with the learning rate. So all the points that are in the top right corner are considered to be good measures of generalization. So what we observed is that E alpha, positive magnitude, we here evaluated it with two different values of the scale parameter, both with a very small value and with a value of root n, where n is the number of training points. And we observed that the majority of these topological complexities lie in this perfect square. And what we also noticed is that the persistent homology dimension is not performing so well. The other question we asked is, okay, are we consistent across different algorithms? And the answer is yes. So if we use HGD or ADAM or RMS-prop, we still have the same performance. So our framework doesn't depend on the algorithm. Here are some further results where we look at the actual generalization gap on the x-axis, and on the y-axis, we plot our topological complexities. And here we run experiments with 6 different values of the batch size and 6 different values of the learning rate. And what we observe is that for E alpha, we have a really nice correlation between the generalization gap and E alpha. Similar thing, it's a different pattern, but still it's quite good. We notice this correlation between positive magnitude and the generalization gap. And we also just computed magnitude, and it still correlates well. And pH dimension is not performing as well. So our main observation here is that our topological complexities correlate well with the generalization gap. Here is another slide of results. I'm sorry, it's very overwhelming. There are a lot of numbers here, but the most important thing is that here we have provided extensive experiments over multiple different models and datasets and domains. And what we see is that our measures are consistently outperforming the persistent homology dimension and also other measures from literature. And we base this on the average granulated coefficient. So we notice here that this is happening across different metrics, and also we use 2 different loss functions. And we see that the pattern is consistent. So in conclusion, we have proposed new topological complexities, and we have proven topological bounds. We have linked theoretically the alpha weighted lifetime sum and the positive magnitude of the optimization trajectories. And we have verified our results across a number of different industry level models and datasets. Now, how do I think? I wanted to briefly mention this work too. So this is another application of magnitude. What is interesting that in contrast with previous works where we were focusing only on magnitude at 1 scale, here we are using the full magnitude curve for application. So here we are like unleashing the full potential of magnitude in a sense, because we are looking at a multi-scale summary of the space. So here I wanted to emphasize one interesting result, as I won't have enough time to go through in details this paper. But we wanted to see if we can measure curvature with magnitude. And what we did was we followed the experimental setup in Turkish et al., where they are using persistent homology to predict curvature. And what we see, what the experimental setup is that we sample 100 different, we sample points from surfaces with constant curvature varying between -2 and 2. And we compute the area under the magnitude curve, which we deem mag area. And what we notice is there is a clear pattern between surfaces of positive and negative curvature. And also there is a pattern where curvature is increasing or decreasing. And what I wanted to point out is that after only using one single feature and using either quantile or piecewise linear regression, we are getting lower mean squared error compared to previous approaches. So I thought this was really interesting. Previous approaches based on persistent homology. And there are a lot more results in this paper. Basically, we measure diversity across latent space representations in a wide range of scenarios across text embeddings, graph embeddings, and we also empirically verify the stability of magnitude. But for more details, please look at the paper. And one thing I really wanted to mention in the end was a bit of a different application of magnitude. I just wanted to say in this work that we have looked at the surface of the human tongue. This was the first work evaluating human papilla in 3D scans and using topological data analysis. And what we established was that characterizing the shapes of these structures is really important, and it can help us say that tongue prints are unique. And in this work, we're also looking at how we can quantify the spatial distribution of these points on the tongue, on these structures, using magnitude. And we think that magnitude would be a very good candidate for such a summary. Sorry, it is a collaboration with Rayna Andreeva from the University of Leeds. Yeah, thank you.
Right, thank you very much. Rayna, you don't have to continue, of course, if you don't have additional materials, but if you want, you can use more time, of course, right? We have allocated more time for the talk, and you mentioned that you had some additional results that you wanted to show, or are these already included in the current project that you showed us?
Yeah, they're already, like, the high level is already included. I think if I need to go into detail, it's going to take too much time. So yes, I think better to.
No, that's all good. Okay, thank you very much. Then thank you very much, and let's all briefly unmute and clap for Rayna's talk. All right, thank you so much. So, do we have any questions from the audience?
Maybe Sang-Kyung, you can go ahead and ask your question.
Hi, good morning. Thank you for your talk. I'm having a bad hair day, video off. I have just a vague question, generic questions coming from someone kind of knows a little, but not too much. The question is, what is the current gold standard? In the sense that I think your talk is about you're trying to develop or introduce a new way of measuring something. My question is that what is the current gold standard to measure that thing?
Like, can you, like, in what sense do you mean?
Something about neural networks. You're trying to develop some kind of way to measure something about neural networks, and if that's a correct,
Yeah.
how are other people currently quantifying that?
Well, in terms of topology, they're using fractal dimensions, and I'm comparing only. Wait, sorry, 1 second. So when looking at the training trajectories, the other work using topology is using the persistent homology dimension. So here we are comparing against how our methods perform compared to that. But if you are asking about other ways outside of topology to measure, I don't know if it's a fair comparison.
Okay, even that helps. Even that helps. Thank you. That helps.
You're welcome. Thank you for your question.
There are also other measures, right, to like, for instance, the L2 norm of the last layer and these sort of things
Yes,
that might
right,
also work,
right.
right? Yes. Very nice. So I actually have a follow-up to this one. So what is the reason to believe that the weight trajectories are capable of containing all that information? Because the weight trajectories are not, in a way, they're not canonical, right? So I kind of wonder, I find this fascinating that this works. This is really, really cool. I just kind of wonder where this is coming from.
That's a great question. Well, I guess the observation that there's a fractal structure to them is a way to quantify their complexity. But yeah, I think it's a very interesting question. I'm not sure. I need to think a bit more about it.
Okay, yeah, no, sure, no, I think it's fascinating that it works, right?
Yeah,
maybe you're on to a very foundational principle here in that these things start to converge. There's an upcoming ICML paper that claims that that a lot of neural networks are, if they're sufficiently large, that they're converging to some kind of shared representation, and maybe these trajectories could prove that.
That's very interesting.
Very
If you have a
exciting.
reference for it, that would be really good.
Yep, I will send those over. Yeah.
Thank you.
Do we have any other questions from the audience?
There's a
I
hands
think we
up
have
by,
one. Yes. We also have one
there's
in the
both.
chat, or is it the same person?
No, there's a hands up by Evgenia Lagoda. Maybe you go first.
Hi, sorry, I will also keep my video off. Thank you for the wonderful talk, Rayna. I maybe missed it. So magnitude dimension depends, like the computation of it depends on the number of points you consider, right? Like, how does it, if you could just say a little bit about how it depends, if it depends.
Well, magnitude depends on the number of points. The dimension doesn't. Yeah, okay, I can. Yeah, one thing I didn't mention about magnitude itself is that. Sorry, one second. So that the limit of magnitude as t goes to infinity recovers the cardinality of the set. Is this the? Does this answer your question?
I guess. Yeah, I don't know. It was not a very well formulated question.
Oh no, it's okay. Yeah, feel free to email me or to ask me afterwards.
Thank you.
Thank you.
We also have another question in the chat from Artyom. Please also feel free to read this. Otherwise, I'm going to do it. Artyom, do you want to unmute briefly? Okay, then I'm just going to read it. So forgive my naive question, are the worst results for larger magnitude, dimensions, and others as well somehow ideologically related to overfitting? It's a very, very intriguing question.
So are there, did I understand correctly, are there any results to link magnitude with overfitting?
No, are the worst results that you're observing for larger magnitude dimensions, are they somehow related to overfitting?
So here, what do we have? So yeah, we had, but basically, one of the points here is the way these experiments are done is we first, in the training trajectories, we first reach convergence to 100%, and then we run more, like, I didn't say that, sorry. We run like 5,000 more iterations of the algorithm. And we compute the magnitude dimension of that. So, Yeah, so that's interesting, but I'm not sure how we can measure. You can measure that using magnitude dimension. Yeah, I need to think a little bit more about it. But a very good question.
Yeah, feel free to also extend that, Atyom, if you have additional questions there. All right, do we have any other questions from the audience? I think Simon has a question. Please go ahead.
Hi, thank you. Thanks for the talk. Nice to see
Thanks.
you all over the place. So I probably have lots of questions, but I'll try and restrict to one, which was about positive magnitude. So positive magnitude, is that just that? So that's not maximum diversity. So that you're just throwing negative weights away, are you? Is that?
Yes, exactly. That it's not quite. Yeah, it's not maximum diversity. Was maximum diversity defined as like the largest magnitude of the? How is it defined again?
Yeah, so you look over the subsets that just have only have positive weights. Yeah.
Yeah, we thought about this, but this is going to be computationally quite expensive.
Oh yeah, absolutely. Yeah.
So we reverted to the simpler version where we just throw away the negative weights. Maybe one other way would be to just take the absolute value of the negative weights, and I don't know what that is going to recover, but it could be something useful.
So right, okay. So this was sort of just a pragmatic thing, was it? Or, I mean, yeah, I'm kind of intrigued as to why you were interested in that, and yeah.
Well, because there was because we wanted to prove generalization bounds, and my collaborator Ben, I don't know if he's here, he found a really good proof, but only when you consider the positive weights. So this was the idea about it. And then we also thought that positive magnitude would coincide with magnitude itself for high enough values of t. And in fact, we observe in our experiments that that magnitude performs quite similarly to positive magnitude in quite a lot of cases.
So I guess that depends. So I don't have a great intuition for the kind of data that your data is kind of low dimensional, isn't it? It's like some kind of fractal curve. Is that the intuition?
Well, the original data is very high dimensional space, but it lies on a lower dimensional manifold. So we are looking at that.
Yeah, because I mean, so you tend to get negative weightings, very very strong negative weightings when you have things like what do I want to say, sort of bodies with non-empty interior. You get sort of these sort of negative weightings near the boundary. But I guess, yeah, if you're more sort of curvy, then I guess I would expect fewer negative weights in that case. Yeah, so it's sort of interesting.
Yeah. In fact, sorry, I didn't mention it here, but there's one plot in the paper which compares exactly the behavior of magnitude and positive magnitude. And and we actually we should do more extensive computation on this, but we noticed that in our case, for the spaces we are looking at, there aren't that many negative weights. So that's why we consider that maybe it's not such a bad idea to ignore it. But yeah.
Cool. Nice. Thank you.
Thank you so much for your questions.
Right. We still have one question in the chat from Marshall. Do you want to read this out, or should I do it?
Hang on. I suppose. I'm happy to read it. I can do at least that. So I come to this talk with a lot of experience with persistent homology, but not much else in the talk, topology, etc. What's the first paper I should read? And then are the slides of this talk available?
Sorry, so your question is, what is the first paper you should read, and
yes,
would the slides be available? Yes, the very first paper about magnitude is the magnitude of metric spaces by Tom Leinster. Yes, I can send you the slides. I'm not sure if they can be uploaded on the ATRN website, but I'll be happy to share the slides with you if you send me your email.
Oh, okay. Thank you.
Thank you.
Yes, to clarify, we don't have a good way of sharing these slides with presenters. Maybe we should be having such a way. We can we will discuss this because such requests do turn up every once in a while. So if it works, please please just exchange that via email. But that's great. Thank you very much.
Thank you.
Right. Do we have any other questions? If not, then I'm.
Oh
then
wait, sorry.
let's think.
Quick question.
Right,
Thank you. Rayna, that one slide, something about this equals this equals that, therefore these two must equal. Do you know what I'm referring to?
Yes. Yes, this one, is it this one?
Yes, this one. My question is this: looking back in retrospect, why wasn't this obvious from the beginning? You know, how could this have made it faster? Any guess?
I mean, which one of the results, like the last one, or maybe just because people were working, the people who were doing these proofs were working from different perspectives, so maybe they. No, but yeah.
I see different perspectives. Okay,
But
got it.
I mean, like, this is not. It's a kind of easy follow up because they're all equal to the Minkowski dimension. So.
Okay.
Yeah, I'm not sure. Good question.
Okay, thank you.
Welcome.
Right. Do we have any other questions? If not, then let's thank Rayna again before we move to the offline session of the talk. Thank you very much, Rayna.
Thank you so much for inviting me.